and battery electric and hydrogen. So if you look at all this ownership over the years, hydrogen, it does make sense and will be biggest cost saving for heavy duty vehicles. And this does not include carbon tax, which is going to come soon. So there is definitely a way by New Zealand, we already, I'll show you pictures later on, we already introducing hydrogen truck. So we calculated that even by 2025, being truck available to replace the existing long range heavy duty, you're going to save a lot of cost in the hydrogen trucks. So this is a model which we have been working on it, just a snapshot, and we are looking for the other transport sectors as well. So then in the platform, we also, we wanted to create ecosystem. So we are starting with the high school. We are spending a lot of time high school people to make aware of the green energy technologies, and then we are sponsoring them to do some summer internship with universities. Then we also have a dedicated green hydrogen scholarship for undergraduate, postgraduate, then the universities and the research institution and government institution like that. So this is a global initiative which I am leading as a director. We partner with them, and basically we wanted to accelerate the green hydrogen ecosystem. So we did quite a lot of work on that, and the science is focused on non-fuel water because we want everybody to, everyone one day will be able to produce green hydrogen themselves in their backyard using a solar or some sort of wind renewable energy source. So that's my vision, which I'm strongly driving, that by in 50 years time, everyone will be energy resilient. They don't need to depend on anyone else. So this is something because the solar is getting cheaper, so they can easily have a solar panel and small electrolyzers produce hydrogen for the transport vehicles and cooking. So we recently demonstrated that a gas panel replaced with the hydrogen, which 0.2 millibar, that's all, 0.2 bar, that's all you need. We have a pilot project running, and we are already made some barbecue out of hydrogen as well. So there's a lot of real activities happening in our place. In terms of the research, we're focusing on non-pure water on 3 research themes: 3 dimensions, reactor catalysis and direct photocatalysis and plasma catalysis. Obviously, you are aware of the common challenges, the selectivity, energy efficiency. So there is almost 25 PhD graduates working on these 3 different teams and a couple of postdocs. And that's led by many of my colleagues as well. So this is one of our high research activities under the platform, which we have an annual event to share the knowledges with in partnership with the DOE, US, and Germans as well. So that's going on. But just one example on what we are doing under the PVEC, we're looking at the more closely to have a low system complexity and highest efficiency. So we're also looking at practical solar hydrogen production. What are the challenges needed there? Such way, the non-pure water and small hydrogen production that can, if you can improve the solar to thermal hydrogen ratio to 30%, that's a game changer for local hydrogen production. So there's a lot of research activities happening on that. One of the results we recently, one of my colleagues led by ICONN University, probably is working at even peroxides for the hydrogen evolution as well. So there is quite a lot of fundamental science also happening, but we are focusing on this towards the demonstrating a smart technology for producing non-pure water. So as I said, we are creating a lot of talent pool, and we for today's industry problem tomorrow's, and we are sponsoring quite a lot of students and graduates and industry exchanges, which is going very well to create the green hydrogen ecosystem. It's a global partnership. It's not one institution, so that's a great way to bring some new green technology to the world. While we're doing it, we also have a commissioning national facility for people to come and test the hydrogen purity, efficiency, everything. So we got a couple of dedicated online IC, GC, everything for the lab testing and field cell testing, and the industries can come and test the purities as well. So as a national lab, this is something we are doing it now. We just started only March, and this will be available to some of our New Zealand industries, others as well. So the one last thing is, while we are doing it, we have taken one of our regional community, Marae we call it, which is a Maori meeting place or temple, if you want to call it. We want to demonstrate how do we decarbonize that one. So basically, we are putting solar panel and electrolyzers to produce hydrogen to replace the diesel generators and cooking. And this is something we partner with the communities. So we so that they are in a remote, they live in a remote island, I mean remote locations in the city, and then when they currently when heavy rain or something they cut off, so they have to use a diesel generator. So we are taking the first initiative to demonstrate we can decarbonize even region for energy resilience perspective. So we are demonstrating by doing putting solar panels, wind, and having electrolyzers to produce solar panel directly produce electricity for them, and also using surplus electricity to produce hydrogen, store them, and then distribute them for heating and cooking. So this is something, a new initiative we are now using as a model to globally showcase how hydrogen could be used to decarbonize even local communities. So finally, what's happening in New Zealand? You can see there is a lot happening. We have a 4 or 5 fuel stations being built, and 2 of them already are commissioned. There's 1.25 PEM electrolyzers running in 4 places. One is powered by geothermal, one is solar, one is wind, one is hydro, and there is a 1 gigawatt hydrogen production coming up in South Island using a hydroelectricity. Then that's going to be shipped to Japan and Korea. So we have quite a lot of activities happening in the hydrogen space. And as you can imagine, we already running a hydrogen bus. We are talking only green hydrogen. So green hydrogen bus in a biggest city in Auckland, and also the hydrogen cars are starting to come from Toyota Japan to country as well. Hydrogen cars, which and the trucks, Hyundai trucks, which is run by hydrogen. You can see they're they're quite nice to drive. I've driven both to do showcase to my politicians and everybody to believe on hydrogen. So I was driving it as a director in the cities and asking people to jump in and feel about it. So this is something we do because we want to promote the green hydrogen ecosystem. And we most of the time I'm driving that car to give them a confidence to the public as well. So that's so last thing next year, we are hosting the Hydrogen Soul Conference. We will release the website soon. That will be in Wellington, and this will be more R&D industry conference, R&D as well. So you're most welcome to come. Thank you.
Thank you, sir. That was a very interesting talk on green hydrogen technology platform. The session is now open for questions. The session is open for questions. You can also alternatively post your questions in the chat box. So meanwhile, I have a small query that you mentioned about tungsten carbide as an alternate for platinum catalyst. So you mentioned that instead of like high temperature process, we can try to get it with ion implantation. So I just want to know, ion implantation, does the tungsten implantation, the phase formation is complete?
Yeah. So we found successfully the phase you need for highest activity, and for junction and molybdenum. Implanted molybdenum tungsten into carbon.
So no other post-implantation processes are required?
No required. It's about how you optimize the implantation parameters. And yeah, so there's a bit of trick there. But we have demonstrated it is possible. At the moment, we are in the patenting process. That's why we are not publishing anything. But soon we will be publishing something after the patenting process.
So you start with carbon foil and then put in moly or
tungsten. Yeah, that's what we do.
Okay. And it is also scalable, right?
Because ion implantation is scalable.
We can scan the stage and that was a quite interesting piece of work. Are there any other questions? Okay, if there are no questions, we can thank our speaker, Professor John Kennedy, for giving us a very interesting talk on hydrogen economy and what are the classifications, the color codes and everything, which is very recently evolving. Thanks for giving a very nice overview on the hydrogen technology platform. Thank you, sir. Thank you very much.
Thank you. Good luck for the conference.
Yes, sir. Thank you. Thank you very much. Sir, good morning, sir.
Yes, Amma. Good morning. How are you?
Yes, sir, I'm good, sir. Thank you, sir.
Thank you.
Yeah, thanks for coming over here. And
Thanks
can we
for
start, sir?
Yeah, please, because I have a hard deadline at 10 o'clock.
Yes, sir, I was told about that.
Yes.
Yeah, thank you, sir. Let's see. I will quickly introduce you. So we are in the next keynote lecture of today's morning session. Professor M.S. Ramchandra Rao from IIT Madras is here with us to deliver this keynote lecture. He's an institute chair professor at the Department of, and also professor at Department of Physics, IIT Madras. His research interests vary from nanomaterial, physical properties, transport properties, magnetic nanoparticles and magnetic tunnel junctions, syntronics, and nanocrystalline diamond films. And some of his awards and achievements include he's a fellow of Institute of Physics UK and Erasmus Mundus professor at the University of Montpellier, France, and University of Rennes, France. And he's a Dart professor, visiting faculty at Walter Meissner Institute, Germany. Also, he's a visiting faculty at the Department of Physics, Shibaru Institute of Technology, Tokyo. He's a section editor for the Journal of Physics D Applied Physics since January 2015. Also, he's head of the DST IIT Madras Solar Energy Harnessing Center at IIT Madras. And he has incubated a company in Research Park, IITM Research Park, on the technology developed with diamond coating. Also, he's Alexander Van Humboldt Fellow and JSPS Fellow. With this very brief introduction, I request Professor Ramchandra Rao to deliver a talk on exploring quantum spin in wide bandgap systems. Sir, can you?
Thank you. Let me just share my screen. Can you see the screen?
Yes, sir, yes.
Okay, so good morning, everyone. And thank you, Professor Karthikeyan, Dr. Sendil Kumar, and Professor Mala for inviting me to ICONN, organized by SRM. It's always a pleasure for me to give seminars organized by SRM, and I hope next year ICONN will be in-person one, because I started feeling that online seminars are no more effective. I hope next time we'll have in-person one in your nice big auditorium there in SRM.
Yes.
Okay, so as you can see the title now, exploring quantum spins in wide bandgap systems. So I belong to the physics department and a few centers. One more center is coming up, which is India Center for Lab-Grown Diamond. I'll briefly tell about it towards the end of my talk. Okay, so that's our beautiful green campus at IIT Madras, and what you see on the left top is our center. You're welcome to visit our center when you're in the campus. So the contents of my talk are as follows. I'll talk about defects in solids. Today, it's all about exploring these defects. We may call them quantum defects, spin defects. And then in that process, I'll introduce two different and versatile wide bandgap systems. One is a transition metal oxide. The other one is diamond, which is ultra wide bandgap system. We'll talk about physics of doping, and then some of the examples in the form of actual results obtained on the zinc oxide nanostructures, nanospheres. And the exciting thing about what happens when you dope diamond. Okay. So it's a big group and lots of activities focusing on fundamental physics aspects of doping. And we also see, spin transport through these heterostructures, quantum heterostructures. It's a very exciting work. A lot of physics is involved there, where we use platinum on top of ferromagnetic and ferrimagnetic insulator. You inject spin, and you see how this spin is absorbed or reflected as you rotate the magnetization of the magnetic layer. So then you measure the spin angle, and in one way you're measuring the Hall magnetoresistance, or we call it the spin Hall magnetoresistance. I won't have time to go into all those details. Today's talk will be mainly focused on zinc oxide nanospheres and diamond. I've chosen as a comparison for these two extremely exciting wide band gap systems. So talking about quantum materials, we know that the quantum materials, in summary, are those, most of us are working on such systems, materials exhibiting superconductivity, magnetic order, can be termed as quantum materials. So there's nothing new about quantum systems, except for the new class of systems, which we call them as 2D systems, 2D materials, graphenes and now MXenes. These are Dirac electron systems. And then when you look at the collective properties governed genuinely by quantum behavior, like ultra cold atoms, cold excitons, polar electrons, and so on. So the common thread basically is what we call it the emergence, quantum emergence. Okay. There was a special issue. If you're interested, you can go through this JFISD special issue, in which there are lots of nice articles on many of these systems that you see listed here: spin orbit interactions, many body interactions, topology, unconventional superconductors, and so on. So now you must be seeing a lot about utilizing, talking about quantum computing. Of course, we are really far away from realizing quantum computing. The fundamental requirement there is to get a quantum bit, a qubit, which is a basic unit of information in a quantum computer. In contrast to a binary bit, that can only have 0 or 1 states. We know that all this has come from the well-known Boolean algebra, Boolean logic. A qubit can be in any coherent superposition between 2 quantum states. While it's a long way for us to probably practically realize a quantum computer, it'll happen, I'm sure, maybe 10, 15, 20 years. But then the basic understanding of theory and experiment is absolutely important. People are talking about quantum computing with defects, quantum computers based on color centers in diamond. Color centers, again, are defects. There's a lot going on using spins in semiconductors for quantum computing. Well, as on today, we have qubits, quantum bits made out of superconductors. And then people have even shown 2 superconducting quantum bits communicating with each other over a certain distance. But then these qubits, for that kind of communication to happen, these qubits have to be really cooled down to millikelvin temperature. But as solid-state, experimental solid-state physicists, always looking at the properties induced by dopants in crystals, we are fascinated to see what happens when you dope different elements in wide band gap systems, because most of the wide band gap systems, as you know, are amenable to doping. Okay. There was this nice paper by David Ashlam's group. He talks about exploring defects in most of the wide band gap semiconductors that we work on, starting from cadmium sulfide, zinc oxide, silicon carbide, diamond, and so on. You see the band gap change from zinc oxide to diamond is almost 2.2 electron volts. And of course, we have been working on these systems because these band gaps, these materials with these wide band gaps are absolutely amenable for doping. Okay, so it's all about point defects because why doping? Well, in principle, a wave function of an isolated atom would provide a very intuitive and well understood quantum state, which you can call it a qubit. That's why spin defects are so important. But then you cannot incorporate isolated atoms in devices. No, exceptions are ion traps and optical lattices. So point defects or dopants in semiconductors are the way to go. And it's very exciting and fascinating to see how an insulator transforms into a semiconductor metal, and sometimes even superconductivity sets in just with doping by certain elements of the order of anywhere from 3 to 5 to 7 atom percent, right? So what happens, of course, then you put these defects in these solids, then you have several characterization techniques like ESR, optical spectroscopy, photoluminescence, and of course, if you are looking at seeing changes in the conduction processes, then you have to do Hall measurements and also electrical conductivity. So typically when you take a lattice and replace, I'm showing a lattice of diamond here, which is made up of carbon atoms, and replace it with boron, it induces a hole into the system. In a similar way, when I replace carbon with nitrogen, I bring in an additional electron into the system. So I can make a p-type material, p-type diamond when I dope it with boron, and n-type diamond when I dope it with nitrogen. But then the interesting thing is, along with nitrogen doping, if there's a neighboring vacancy, if the neighboring vacancy pairs up with the nitrogen that replaces the carbon, you'll have this NV center. That's a fundamental building block to realize room temperature quantum dots, right? This is very exciting. Why? Because if you look at spintronics, well, we normally talk about the conventional electrons does not use the spin of an electron. We only talk about charge transport. Electron has 2 degrees of freedom: the spin degree of freedom and the charge degree of freedom. And we always talk about charge transport, and then it is always exciting to use the spin degree of freedom of an electron. And as you know that it's 100 years of Stern-Gerlach experiment with very limited resources. Stern and Gerlach could confirm the quantum nature of electron spin, which is a fundamental quantum entity, as we know. And today we know that spin has 2 possible orientations in the direction of an applied magnetic field. We talk about upspin and downspin, or spin half, and in terms of magnetic quantum number MS, it is plus half or minus half. So based on this, Mott came out with this beautiful Mott's what is called this 2-spin channel model. I'll be in brief terms, you experimentally one can realize Mott's 2-spin channel model by creating these multi-layers. Okay, I can create one layer that has high resistance, the other layer that has low resistance, and then when you look at the difference, that is delta R, and that is delta R is what is required in certain devices, called magnetoresistance devices. You have systems that are highly spin polarized, marginally spin polarized. Iron, cobalt, nickel, and copper are marginally spin polarized, where the spin polarization is anywhere from 11 to 40%. But you also have compounds like chromium oxide, which should give you 100% spin polarization. Porcelain alloys give a very high degree of spin polarization. What happens is you'll see the Fermi level lying in one of the completely filled up or down bands, whereas one of the bands is completely empty. The other band is completely full with upspin or downspin electrons. That leads to 100% spin polarization. This has led to a great activity in the last 3-4 decades. You have the GMR, giant magnetoresistance, tunnel magnetoresistance, and the concept of spin valves, where you see that I can deposit a ferromagnetic layer on an antiferromagnetic substrate, which means the magnetization on this layer can be completely pinned, so you don't let it move around. So you have an insulating barrier. If you bring a ferromagnetic layer on top of it, in order that the energy of the system is minimized, the magnetization of this layer will be opposite to this one to start with, and then you apply the double arrow is shown there because I can use a small magnet to manipulate that magnetic spin, right? So this we call it the spin-dependent tunneling process, and that has led to the evolution of the GMR devices. What happens is I use a small magnet, and I can rotate the magnetization of the small, the top layer, and this leads to this beautiful concept of the spin valve. So you're using it like a valve. Open it, close it, make it highly resistive, multilayer, and low resistive multilayer. No, in one way I can call it a sensor. You see that? High resistance and low resistance. This is a beautiful experimental demonstration of starting from the well-known concept of Mort's two-spin channel mode. But this has gone a long way. If you now look at strongly correlated oxides, since the last 4 decades, a lot of work is being done on using manganites as tunnel junctions. That means I have a ferromagnetic layer, another ferromagnetic layer separated by extremely thin nanoscopic level of insulating barrier. And then I can control the resistance of the tunnel resistance by controlling the width of the tunnel barrier. So almost 2 decades ago, we've been invited to write this interesting article. At that time, the well-known Julia's formula, Julia's formula never considered, when he explained so nicely about the concept of magnetoresistance, for some reason, he didn't consider the nature of the tunnel barrier into account. He didn't take it into account. And our paper clearly shows that the tunnel barrier plays a crucial role in determining the tunnel resistance. And what we showed was one is able to get magnetoresistance by creating these artificial tunnel barriers. But then if you look at the highly nonlinear IV characteristics, which are evidence for non-ohmic transport mechanism across the artificial grain boundary, which is the tunnel barrier, it's very clear from the models proposed by this Russian group long back that the conductance is, expected to be largely dependent on the nature of the tunnel barrier. So this prompted us to, for some reason, for many years, all the experimentalists were using strontium titanate as a tunnel barrier. We went ahead and replaced it with an insulating manganite itself. That means if you take LBMO, which is typically a ferromagnetic metal, you overdope it with transition metal element, at a certain concentration, it becomes an insulator. So we use that insulator. Now, the good thing is you have all the three layers which are manganites. The insulating layer is also a phase of manganite. So you have an extremely good interface. And we were the first to show how a nanoscale insulating barrier made out of a non-strontium titanate layer could be used as a tunnel barrier. And of course, later, a few years later, Stuart Parkin came out with this wonderful work on using magnesium oxide as a tunnel barrier, and he came out with the extraordinary magnetoresistance, and that technology went to Hitachi in making those magnetic tunnel junction devices. And you see, pulse laser deposition could be used to make all these excellent quality tunnel barriers. And you see the interface here between strontium titanate substrate and LBO. Same would be the case with LBMO also. You see a very clean interface, and such interfaces could be obtained, especially when you're dealing with oxide materials, only with a technique like pulse laser deposition. And this has opened up a new field called adaptive oxide barriers for efficient magnetic tunnel junctions, because once people have started realizing that the tunnel junction plays a very important role, it's not just that strontium titanate alone should be used as a tunnel barrier. You talk about the matching of electronic wave functions according to the symmetry rules and so on. People have started using all kinds of tunnel junctions, copper oxide, hafnium dioxide, zirconia, even some of these PCT materials and so on. And this also has led to scientists thinking that, how about using non-oxide layers like aluminum nitride and diamond as potential barriers? So this has prompted us actually to take up work on diamond, but it's a very, very challenging thing. While you grow oxides using a technique called laser deposition, diamond requires much higher temperatures to get into thin layers. But of course, the whole thing has led to a new kind of research in our lab. So coming back to this, I'll talk about first what we have done with zinc oxide, perfectly exciting system. One thing I would like to say is doping in zinc oxide. For many years, people have tried to look at magnetism, especially using transition metal atoms like nickel, cobalt, and iron. So we have busted this myth saying that don't talk about magnetism when you're doping transition metal ions, which are already magnetic. The magnetism is not because they get doped and inherently they produce magnetism in those lattices. It's just because nickels and cobalt and iron produce magnetism in the form of clusters in the solid. So this was a very interesting work. My colleague Carlo Lamberti, an exciting scientist from Italy, passed away unfortunately a few years back. But then what we showed was, even though your X-ray diffraction shows that nickel actually goes inside the lattice, but 77% only gets substituted, and the remaining nickel is there in the form of nanoclusters. So the magnetism that you see is all because of these nanoclusters. So it's not true magnetism. So you don't have in order to manipulate spin in a semiconductor, ideally you need a semiconducting lattice with a magnetic ion sitting in it. You can manipulate the spin. You can think of making a spin qubit. But the problem is, even after 25 years of research, the only true magnetic system is manganese-doped gallium nitride. We don't have any a true diluted magnetic system in oxides. So the role of oxides is exciting. We did this article In 2000, it's a 2016 oxide roadmap. There are some really beautiful articles written by all the big names working in oxides, including Professor Venki and Nicholas, Paldin, Ramesh, and so on. And then just to show that, one article clearly shows that, even today, zinc oxide is still an exciting material for LEDs, displays, UV detectors, sensors, and so on. Why oxides? Because of the ability to provide a plethora of tunable properties in terms of mobility tuning, low processing temperatures. You can't beat oxides when it comes to you want to have a device with a certain mobility, and then at low processing temperatures, we have a clear choice of several types of oxides. That's the advantage of oxides, and today we also talk about zinc oxide could certainly be used as a UV detector. Where gallium nitride stops, zinc oxide takes over, right? And zinc oxide is a very good material for plasma enhanced whispering gallery modes, and tin oxide also. It's a material that could be easily deposited, using even spin coating techniques, and we showed that flexible MOSFETs could be made with tin oxide. A few slides on some interesting work that we did on zinc oxide. Well, it's all well established that zinc oxide nanorods could lead to lasing action. But then the other part of the story is when you make micro cavities of using these metal oxides, especially zinc oxide, what happens is you make a micro cavity. Whispering gallery modes occur when light, when you shine light on these micro cavities, the lights start orbiting near the surface of this dielectric medium, and then after as it returns in phase after several revolutions, at a certain point, resonance occurs, and that resonance is shown up as a strong emission at a particular wavelength, or it can happen at several wavelengths. Mathematically, you can calculate and show for a given material, for its refractive index and dielectric constant, what should be the what are the modes that you expect in that particular metal oxide system. So we grew PLD. It's an extraordinary technique, as you know. You can get extremely smooth layers. You can also get nanorods, whiskers, and all that. And by tuning the conditions, we could get these droplets. Now, normally, you don't want droplets while growing thin films, but these droplets are useful if you pick up these droplets and I excite them with a laser source. What happens is, what was shown earlier was, if you look at this normal emission, photoluminescence emission from zinc oxide, you see a nice peak at 391 nanometers. So zinc oxide shows that photoluminescence at 391. But the moment you look at the PL emission in the form of zinc oxide microspheres, you start seeing the same 391 peak, sharp peak, splits up into smaller peaks. And then you also have, as you increase the laser power, at a certain power density, you start seeing the lasing action. So these are required for low power electronic applications. So our Japanese colleagues actually make devices using the microspheres. You see that, that's what happens. A smooth transition that you expect normally in zinc oxide bulk or thin films transforms into these spiky structures, and when you expand this is what you'll get. The lasing action happens at a very high threshold. So we thought that, see, and you see the visible wavelength region here, right? There's no emission there. There could be defect emission also, depending on the way you prepare these nanospheres. So what we thought was, how about getting these whispering gallery modes in the visible region, right? So how do you get that? So we decided to dope zinc oxide, not with transition in metal ions, but with rare earth ions. As you know, rare earth ions always create these multiple electronic levels in the forbidden band gap of these wide band gap systems. But the problem is, if you take rare earth ions, you really cannot dope large concentrations of holmium, erbium, or samarium. That's because of size mismatch. Because you're looking at 0.72 angstroms of ionic radius of zinc versus 1.018 angstroms of holmium. So the solid solubility limit is very low. But then we could manage to put and get a pure holmium doped zinc oxide and other rare earth ion doped zinc oxide at very low concentrations, not more than 1 atom per cent. But that was sufficient enough for us to exploit the, all these mid-band gap states that are created in the zinc oxide forbidden gap. And this is a clear proof when you do a simple absorption or reflectance versus wavelength, you clearly see the presence of these mid-band gaps, right? So more clear in the case of holmium. I can even identify the levels corresponding to those absorptions. No, this is wonderful. So this is proof enough that holmium is going inside the zinc oxide lattice. And then we made those microspheres out of this holmium doped zinc oxide. And then this was a very interesting paper that we published. What happens is, while we saw the whispering gallery modes in the pure zinc oxide without doping in the UV region, by doping holmium, you start seeing whispering gallery modes in the otherwise flat intensity response in the visible light region. This is exciting. This is the first time whispering gallery modes could be seen in the visible region in doped zinc oxide. And the very interesting thing is the lasing threshold here is, in the case of holmium doped zinc oxide, is just 32 kilowatts per centimeter square, whereas in the pure zinc oxide, undoped one, it is almost 1 order more in order to get the lasing action. So you can make low power lasers in the visible range using zinc oxide nanospheres, or microspheres rather, using doped zinc oxide, right? So this is a very exciting work. So with all this, our conclusion is zinc oxide may not be the best material for quantum applications, but you can see exciting light emission properties using zinc oxide. So one of the things that was mentioned is about quantum computing, because quantum computing requires defects that are uncorrelated. You don't want any decoherence happening between two defect states. But then zinc oxide is a different kind of lattice that can be explored for other applications. May not be straight away good for quantum computing applications. And then you have, of course, another exciting lattice, that is diamond. And one of our centers' mandate is to make these NV centers. As I told you in the beginning, it's a long way to go, but the physics of this doping is very exciting in diamond. One needs to get NV centers in a very, very aligned manner crystallographically, and they have to be separated from each other, neither too far nor too close. You don't want the quantum decoherence to happen. So these challenges we are addressing, but the big thing that we are yeah, okay. Before that, I don't want to go into these details. In addition to zinc oxide being a good material for producing emission using whispering gallery modes in the visible range, we also use zinc oxide layers, ultra thin layers, for looking at the spin transport, observing the spin transport phenomenon. Okay, now diamond, if you make a quick comparison of diamond with graphite, it has You know that it's a cubic diamond structure. It's more dense than graphite. It is a good a transparent material, and it is the hardest material ever known. The hardest material that you can think of. The best part is, even though diamond is an electrical insulator, its thermal conductivity is very high, almost 4 to 5 times more than that of copper. Where is the thermal conductivity coming from? We know that in metals, the electrons carry the thermal energy, and thermal conductivity contribution also comes from phonons. So in diamond, which is devoid of free electrons, all the thermal conductivity contribution comes from the strong phonons that are present in this lattice. So our Quantum Center for Diamond and Emergent Materials focuses a lot on material development, understanding the key physics aspects. So my colleague Praveen does ODMR experiments, and our engineering colleagues work on using these membranes for sensor applications. And we're also aiming at, squid applications using superconducting diamond. Okay. Now that's where this aspect of using diamond, especially to explore the doping aspects in diamond, become very interesting. But before that, this is a fantastically exciting material. You can use diamond coatings for machine tools. That's how we started all this work parallelly with all the oxide work that we do in our lab more than 15 years back. Of course, diamond has this, it's a gemstone. It's the best gemstone. It's a very expensive one. And today, our center is actually focusing on making even lab-grown diamond. It's a good thermal conductor. It's a great optical material. It is required for quantum circuits and future electronics. All these applications are there. You can make transparent windows. You can make windows for synchrotron applications. And we started this work as getting diamond in the form of coatings on cutting tools. Chennai has a lot of automobile industries. And one of the industries, the Murugappa group, came to us with a requirement to save the life of their mechanical components. And normally, mechanical wear resistance can be prevented by using hard coatings like carbides, nitrides, typically titanium carbide, tungsten carbide, etc. But there's nothing like diamond coatings. So that's how we started this work. It's been a very successful work, and that has led to many other applications. And towards the end, I'll explain about this very excellent societal work of using diamond electrodes for water purification. Okay, that's what we do. Diamond can be grown in 2 ways. It's a CVD process. We use hot filament CVD when it comes to applications related to coatings on machine tools for mechanical wear resistant applications, space applications, where you see the formation of these crystallites. All these crystallites agglomerate, and you see the formation of these layers. So we can control the grain size and call these structures microcrystalline diamond, nanocrystalline diamond, and ultra nanocrystalline diamond. All this depends on the kind of application that you're looking at. Okay, but then if you want electronic or optical grade diamond, you need to go for microwave plasma CVD in order to eliminate the possibility of any defects. Okay, but diamond also can be grown using high pressure, high temperature technique. This is a big challenge. We are going to take up this challenge also to build machines for making high pressure, high temperature synthesis. That means you need high pressures of the order of 5 to 8 gigapascals. As you know, diamond grows 60 to 100 kilometers below the Earth's crust, formed over millions of years under very high pressure and high temperature conditions. Those conditions have to be simulated in lab environment. Yeah. So just to show that, this is a commercial setup we have now. We've got an indigenous setup built in India to do the same thing as this commercial one was doing, and at almost 1/5 of the cost. And the good thing is when the crystallite size is very small, you even start seeing a 5-fold symmetry. Normally in crystal growth, 5-fold symmetry is forbidden, but this happens only when the crystal size is below 400 nanometers. After that, the 5-fold symmetry vanishes. Okay, and we can coat this diamond on a 12-inch wafer extremely uniformly. That's not a problem. And SAW devices, you can make diamond for hard coatings, thermal spreaders, and of course quantum application. There are many more applications like this. We also work on diamond for many medical applications. We work closely with, just a minute. Okay, so we also worked with a dentist in Chennai, where we coated. Diamond is also biocompatible, so it provides mechanical wear resistant coatings. It's also hard radiation resistant. It is corrosion resistant, right? And it can be used as a thermal spreader and so on, right? So diamond coated on body implants, we showed that there is no bacteria formation even after 3 months. Of course, these dental implants are made of titanium, which itself is biocompatible, but then diamond coatings are required to further enhance the longevity of these coatings. Another great application of diamond is, studies show that nearly 2 billion gallons of cutting fluid is used every year for machining applications. And where is all this fluid going? It's going into water bodies. And how to eliminate that? Now the emphasis is on dry machining. But how do you dry machine if you can't take the heat away? Yes, heat can be taken away if I have a coating which serves as a lubricant, and also which serves in dissipating heat away. And that's where ultra nanocrystalline diamonds are useful. You don't need the fluid. It serves the purpose. It also prevents the wear resistance of this tool. It increases the longevity. We have shown that these tools can be, the life can be increased by 10 to 12 times, 12 to 15 times even. And then because of the high thermal conductivity of diamond, heat dissipation also happens. Okay. And then for all these technologies in 2019 and 20, we received the Dare to Dream award initiated by our Prime Minister. From about 1,200 entries, they chose 12 for final presentations, and ours was chosen as a group that, our proposal for technology developments has been judged as the #1 winner in the country. The very next year also, we won another award based on another technology we proposed on diamond coatings. All right. Now coming to the physics part, if you look at this chart, as always, we are interested in the doping effects. And on this chart, you see the predicted technology is hello?
Hello, sir.
Sorry, I lost you. Yeah.
Yes.
So the exciting thing is about making diamond superconducting, and how does it happen? Of course, that happens with doping, and then you can dope diamond with boron, nitrogen, phosphorus. Well, anything beyond boron is always challenging, even though all these elements can be doped. During the growth process, you can straight away dope diamond with boron easily. And nitrogen and phosphorus can be doped at lower concentrations, but for high concentrations, you need to go for, implantation. Because you see, what happens is when you dope boron, it creates a donor acceptor level at 0.37 electron volts above the valence band. And if you start increasing the doping levels, this acceptor level becomes a band. And at some point of time, this band overlaps with the valence band, and then conductivity kicks in. And that makes a insulator to metal transition happen. All the way the insulator transforms into a semiconductor, and even superconductivity happens at a certain concentration. And that's what happened. And thanks to our student Dinesh, it's very unfortunate that this young boy 2 years back succumbed to a deadly cancer. But all this hard work was done by him to establish superconductivity in diamond at these very high concentrations. You get a superconductivity at about 6 Kelvin, 6 to 7 Kelvin. The good thing about this superconducting transition is even in a magnetic field of 5 Tesla, superconductivity is not lost. It is just not lost. The transition decreases from 7 Kelvin to 2.4 Kelvin, but then it is there, which means you have very strong pinning centers. So this is, yes, so the superconductivity is clearly confirmed. Well, always when you want to confirm superconductivity, specific heat measurement is the one to unequivocally prove the presence of superconductivity. This cusp means superconducting transition, superconductivity is there in this system. And just a word about granularity. Now, I talked about microcrystalline, nanocrystalline, and ultra nanocrystalline diamond. Of course, the grains are superconducting. The grain boundaries are not. So this can be used for a very specific applications, So one of my collaborators in College Park, Maryland, Professor Anlage, who does this kinetic inductance studies on various superconductors. Look, in simple terms, if I have 2 quantum bits, these 2 quantum bits have to be connected with a superconductor, but a superconductor that has high kinetic inductance, so that the data that is transmitted is not lost. So that's the principle of high inductance. And high inductance happens in granular superconductors only. And what are the systems that are used? You just have a handful of high inductance superconductors like titanium nitride, niobium nitride.
I'm sorry to disturb.
Pardon?
Sorry to disturb, sir. Like, yeah, time is almost over.
Yes, 2 minutes, huh?
Yes.
Yeah. So,
okay.
So what they found was the penetration depth was almost 4 microns, and which means, and this boron doped diamond also has very high microwave inductance. And in fact, Professor Anlage says that boron doped diamond now could potentially replace all the existing conventional granular superconductors, and then it can be called a new granular superconducting material that can be used as a perfect connector possessing high kinetic inductance between 2 qubits, in quantum circuits. All right, I think I'll stop there. I probably will talk about all the other applications of diamond. So since you can also make diamond conducting, we can make conducting diamond electrodes to purify water contaminated with all this industrial waste, dye contamination, pharmaceutical waste. All these effluent can be treated with diamond electrodes. I think I'll stop there.
Yes, seriously.
Thank
Very
you.
quite interesting talk on zinc oxide and diamond-like carbon films. And thank you for sharing all the work that you have been doing for quite some time on zinc oxide and diamond. If there is a quick question, then we can interact with Professor Sir, before anyone asks, I have a quick question. You talked about zinc oxide, the multiple emission at multiple wavelengths,
Yeah.
and the intensities are quite different. Is it possible to maximize the intensity at a particular
No.
wavelength?
No, the intensities depend on, see, if you mathematically calculate, you'll exactly see, these are like X-ray line intensities. You have a peak with the maximum intensity because you have more number of atoms in that particular plane. Well,
Okay.
it's an analogy.
Central one.
Yeah, you'll have maximum intensity line and other peaks that are of different
Symmetrical.
intensities. So if you want to make a device at a particular wavelength, let's say at 460 nanometers, 520 is giving the highest wavelength, and you can make a device pertaining to that particular wavelength.
Okay. So is it possible that it can be shifted to other parts? Because you said in the entire visible region, we will be able to.
So in the entire visible range for a given refractive index and dielectric constant, let's say you get 4 or 5 lines, and the positions of those 5 lines are fixed.
Okay.
Right. But if let's make a device and functionalize this microsphere with an organic matter or a biomatter, you may see a shift in that peak. That's how you use it as a low power electronic sensor.
Okay. Okay.
Yeah, that shift or intensity change can be correlated with, for your sensing application.
Okay. Okay, sir. Okay. Thank you. Thank you, sir.
Thank you. So,
sir, one quick question Dr. Chandra Mohan has raised. Is there any special requirement one has to consider during the doping of diamond, considering the high CC bond, carbon-carbon bond strength in carbon-based materials?
Yeah. So the energy formation is very critical there. It's a hard lattice. You cannot make elements to diffuse easily. Nitrogen, boron, it happens, boron doping can be done during the growth process itself, because when the lattice is being built, you push the element and make the carbon replacements happen. But nitrogen and phosphorus can be doped to very low concentrations only. So high concentration levels, if you want to achieve high concentration levels to see what happens to the conduction or conductance, you need to then implant nitrogen and phosphorus and then make the diffusion happens from the defect regions. So it's a complex process. The chemistry of diffusion in diamond is very complex. Yeah.
Okay. Thank you, sir. If there are any more questions, you can directly write to Professor.
Yeah.
And thank you, sir. Thanks for your time. And
Thank
it was
you
a
very
very
much.
quite interesting talk. Thank you.
Thanks a lot. Bye.
Bye. Participants, we have now the parallel session starting. You are requested to join the sessions that interest you. So the parallel sessions are starting now. Thank you.
Thank you, Professor. Thank you, Professor.